So it's actually quite easy to make a buffer. All you need is weak acid and the conjugate base in its salt form. So basically, for example, like if you were to make a buffer of phthalic acid and hydrogen phthalate ion, you need the conjugate base hydrogen phthalate ion as sodium hydrogen phthalate. Buffers are useful at a specific range. This useful pH range here basically just shows what pH these buffers are most effective in maintaining the pH is of whether it's a reaction or, for example, for biological systems. For example, the human blood is actually composed of buffers. Okay, and in some buffers too, like hydrogen phosphate ion and phosphate ion, well, you have to prepare this buffer basically from salts of these two ions. Let's say, for example, sodium hydrogen phosphate for the weak acid and sodium phosphate for the conjugate base. Now, that reaction can actually, or sorry, that buffer can actually be helpful in maintaining a reaction or whatever at the pH of 11.4 to 13.4. So it's appropriate to choose the correct buffer when you're trying to maintain the pH of a reaction. All right. So we will discuss this when we talk about it in lecture. But what I want to go over with today will be the Henderson Hasselbalch equation. So the Henderson Hasselbalch equation is a quick way, well, not really quick, but it's a handy calculation for determining the pH of a solution, of a buffer solution in particular. Okay, there are many forms of the Henderson Hasselbalch equation. In fact, your book actually tells you how it is derived. But for the purposes of this course, we're only going to discuss this form. Okay, pH is equal to pKa plus log of the base. This is actually the conjugate base, okay, over the acid. Okay, and the purpose of this one will be to calculate for the pH of a buffer without having to use the ice table. So again, when we meet online, I'm actually going to discuss how to calculate the pH of a buffer using ice tables. Now, the buffering capacity that I've actually shown you before, okay, it's basically this exact table, is actually a pH range at which the concentrations of the base and the acid are equal to each other, okay, such that log of 1 is equal to 0, so this term cancels out, and you have pH is equal to pKa. So if you know the pKa of the acid in your buffer, that's basically the best pH range at which it works on, plus or minus 1. Okay, now as we will illustrate in some problems today, there are cases in which the pH is actually greater than pKa, or the pKa is greater than the pH. Okay, and again, we will illustrate that in some examples. So let's go and answer these questions. Calculate the pH of the following buffers. Okay, you're given that the Kb of ethylamine, so that's ethylamine, is 5.6 times 10 to the negative 4. Okay, so again, the only form of the Henderson Hasselbalch equation that we're going to use is pH is equal to pKa plus log of base over acid. Okay. Now, since we're given here the Kb of methylamine, or sorry, ethylamine, then we want to determine first what the Ka of its conjugate acid is, which is the ethylammonium ion. Okay, you just add a proton to this. So the ethylammonium ion has this structure, CH3, CH2, NH3 plus. Okay, so you want to know the Ka of this acid, and to do that, we just write Ka is equal to Kw divided by Kb. Okay, and that should be equal to 1.0 times 10 to the negative 14 divided by 5.6 times 10 to the negative 4. Okay, so that should be equal to 1.0 8 times 10 to the negative 11. Okay, let's check if these three solutions that we're going to calculate today are actually conjugate acid base pairs. So we have ethylamine, and we have here ethyl ammonium chloride. Okay, remember that ethyl ammonium chloride actually breaks up into ethyl ammonium, okay, which is, well, what we just wrote there earlier, the top of the slide, plus chloride ions. Okay, so basically what this means is the concentration of ethyl ammonium chloride, therefore, should be equal to the concentration of ethyl ammonium ion. Okay, now again, chlorine being the anion of a strong acid, a very strong acid, does not have any basic or acidic properties. So the only acidic part of ethyl ammonium chloride is the ethyl ammonium ion. Okay, let's work on the first example. Okay, in the first example, we have now just calculated for the Ka of ethyl ammonium ion. Now, let's actually just go back and one thing, this is actually negative 11, by the way. Since the equation actually asks us for pKa, why not at this point let's just get the pKa so that we can plug in a more simpler number, basically something up in scientific notations. Okay, so the pKa is taking the negative log of this value, 1.8 times 10 to the negative 11. Okay, and that should just give you 10.74. Okay, so 10.74 is the pKa of ethyl ammonium. Okay, so from there, let us calculate the pH of each solution. Okay, for letter A, again using the Henderson Hasselbalch equation, you have pH is equal to 10.74. This is what we just calculated earlier. Okay, plus log of the concentration of ethylamine, for that case, is 0.5 molar. Okay, then the concentration of ethyl ammonium chloride, which is equal to the concentration of ethyl ammonium ions, is 0.25 molar. Molarity cancels out, and here you have 10.74 plus 0.30, that's equal to a pH of 11.04. Okay, letter B, we have pH is equal to 10.74 plus log of 0.25 molar. Okay, 0.50 molar. This one's going to be equal to 10.74 minus negative 0.30, which is equal to 10.44. Okay, and then let's rewrite that up there because I need some space. 10.44. And then for letter C, that's actually a much simpler calculation because you have pH is equal to pKa 10.74, okay, plus log of 0.50 molar divided by 0.50 molar. Remember that the natural logarithm, or the logarithm, whatever, also applies for natural logarithm of 1 is equal to 0. So this term actually cancels out. Okay, and then we are left here with 10.74. Okay, so there's a few things to appreciate in this problems. Number one, note that in the first problem, you have a pH value, okay, which is higher than pKa. Okay, and as you can see, the concentration of the base, which is the numerator here, is actually higher than the concentration of the acid. So this one again will hold true if the concentration of the conjugate base, let's just write that as Cb, okay, is greater than the concentration of the acid. Okay, not sure why that disappeared. There we go. Okay, and then now for the second case, that's the opposite. You have here pH lower than pKa. Okay, you're comparing 10.44 with 10.74. So this is now if the concentration of the conjugate base is lower than the concentration of the acid. Okay, and then for the last case, you have equal concentrations of acid and base, and what you have here is actually pH is equal to pKa. So pH is equal to pKa if the concentrations of the conjugate base is equal to the concentration of the acid. And it is said that buffers are most effective when pH is equal to pKa. Okay, because remember the effective buffering capacity should be pKa plus or minus 0.1. All right.